All right, I'm going to take a bit of a different perspective. This is not going to be very high level about ChatGPT. This is going to be a little bit about things below ChatGPT and about how you build such a thing. And so I want to give you a very simple example of like how these neural networks work. So I'm going to start with a kind of like a challenge. So there's two images here, and the left and the right are different. And I want you to kind of look at this and see if you can see the differences. They're subtle, but they are there. And I'm probably not going to give you enough time to look, so I'm just going to keep chatting for like the next 30 seconds. And you can kind of look, and maybe you'll see some differences. It's pretty challenging. So I'll just go. So the difference is here, there's an additional star on the left. I think the left is the real one, and the right is not. And there's kind of the house is a little different in the bottom here, right? So the point being with this is that when you try to look at this, you try to look at both images and you try to understand what it's going on, right? This is a Van Gogh, you probably all know, and you see all the brushstrokes, you see the kind of beauty of these images. If I were to tell a computer to do this, what I would have done is I would have taken the two images, overlaid them, and then just gone pixel by pixel and say, where are they different, right? And I would have gone to the same answer, and it would have been very fast, and it would not have thought about, how great Van Gogh is, why is he making the stars swirly, and so on and so forth. But because I made you do this exercise, you now know a little bit about Impressionist art. And I can give you 4 Impressionist work and ask you which one of these is Van Gogh, right? And because you just spent 30 seconds staring at a Van Gogh, you might be inclined to realize that the one on the top right is a Van Gogh, and the others are other great Impressionists. The point of kind of ChatGPT and a lot of the kind of modern machine learning techniques is to kind of teach the AI how to learn these patterns, right? How to actually learn how to understand what Impressionist art is, right? And not just to systematically look for deviations. And so what we learned here was that we can actually be kind of art critics ourselves if we just look at thousands and thousands of images and stare at all the features, and we start to understand how you can construct these things. And that's effectively what these kind of large kind of language models are doing. And so it's, the other analogy I always like to use is like the Karate Kid, right? The best way to kind of learn how to do karate is to sit and wax your car and paint your fence and kind of do things over and over, but actually kind of break down the whole process of kind of being a karate master into kind of small functional kind of problems. And so I want to give you this in the context of physics. So I'll give you a real research example, and then I'll try to explain how we try to teach this. So typically, if you make a machine learning algorithm, right, and I'm sure many of you have done this, you take inputs, you have a neural network, and then you have some sort of output, and often you want to make a discriminator, you separate the two, right? You have signal and background, you separate. What we're going to do now is we're going to make an intermediate space, right? We're going to kind of take inputs, take a neural network, make an intermediate space that kind of sorts things, right? Does some tasks, tries to understand the data, and then we can go and do our downstream tests, like separate signal and background, right? There are many names for this. So let's try to learn this space. So I'm going to take a cat, and I'm going to take a dog, and I'm going to augment these cats and dogs. So I'm going to each give them sunglasses. And these are going to be kind of my wax on and wax off. And so what I'm going to do is I'm going to tell a neural network to build a space where the cat and the augmented cat live in the same region of the space, and the dog and the augmented dog also live in the same region of the space, but these two objects themselves are far apart from each other, right? So the dogs are far away from the cats, and even the augmented dogs are far away from the augmented cats. So you end up with a space like this, where cats live in one side, dogs live in the other. The augmented cat that you kind of modified, you gave it sunglasses, and the augmented dog are very close to each other, right, to the regular cat. But other cats tend, and this is kind of magic, right, they tend to kind of be aligned with these cats just because, just by giving this simple task of, telling you that cats with sunglasses are similar to cats, you end up kind of putting all the cats over in this one region, and you end up putting all the dogs over in this one region. So let me give you a physics example. And so we're going to do a training where we kind of build this space, and I'll show you the space. And then we'll show this in the context of downstream tasks, right? So let's do that. So I'm going to take, in this case, a Higgs boson. Could be any object, any physics. And in this case, what I'm going to do is going to simulate my Higgs boson, and then I'm going to modify the simulation, right? So Higgs bosons, in this case, can decay to showers of particles. It's on the order of 50 to 100 particles. And this showering has huge amounts of uncertainties in how we model it. So you can effectively just re-shower it in a slightly different way. And what I'm going to do is I'm going to tell my machine learning algorithm that the Higgs boson and the re-showered Higgs boson are the same thing. And I want to put these in the same point of the space. So this is actually kind of a more realistic what this looks like. The blue is a re-showered one, and the red is a Higgs. This is some way of saying kind of embedding quantum mechanics in machine learning. You say, well, there's some uncertainty as to how we model this Higgs decay, and we're just going to model all possible final states, right, simultaneously, and embed it into one point in space, right? So here's the case of a Higgs. We're going to do this with other particles, quarks and gluons, and we're going to build a space, right? So we do that, and this is our space, and kind of magically, all the different Higgs bosons, they're all different. These are different decays, different energies, different properties of the Higgs. They all align in one part of the space. And the quarks and the gluons, which are kind of similar on their own right, align in other parts of the space. And actually, the gluons are kind of close to other gluons, and the quarks are close to other gluons. Gluons are close to gluons, quarks are close to quarks. And kind of magically, everything seems to align. And all we did was took the same Higgs or the same quark and gluon and just modified our simulation of that, re-showered it, kind of took a final state that would be kind of consistent with our initial assumptions of what that particle was, right? So we've magically built this space. This is a visualization. It's actually an 8-dimensional space, so it's kind of hard to visualize. And suffice it to say, what we can then do is, if this works and we embed things into a single point, we can take our simulation and take all the uncertainties in how we model the physics and kind of embed it into this space. So here's a variable, well-known variable, where we have kind of large variations if we vary our simulation. So this kind of band here gives you the kind of percent variation that you get if you modify the simulation. And we're going to modify these simulations, but embed it into one space. So this is what you get for this variable. Now we look at the kind of equivalent variable in this space, and the variations are 0, right? And so effectively what we've done is we've taken all our physics uncertainties, our uncertainty in how we understand these things, or even the kind of intrinsic uncertainty from quantum mechanics, we've thrown this into one point in the space, right? So we're kind of teaching a machine learning algorithm how to understand the physics that we know and how to ignore the physics that we don't know, right? And so from that, we suddenly have this incredible space. And now we can start doing downstream tasks on it. And it turns out it's actually better at finding Higgs bosons than kind of the state of the art. We see kind of improved signal background rejection, right? It's kind of independent of our shower models or kind of underlying simulation. But then if we say, well, we just built the space with Higgs and kind of quarks and gluons, but now let's look at it for other physics processes. So we can take, for example, W bosons, so completely different physics process, kind of similar in some ways. And we can ask it to solve problems of W boson discrimination. And we find that we can actually outbeat the state of the art with kind of this intermediate space. So we use this intermediate space as a kind of stepping stone to then solve this problem. So what have we learned? We have learned what is often referred to as a foundation model. This is kind of the guts of what these large language models do. We built an intermediate space that understands physics. And we did this by giving it kind of physical rules for how to learn. And we gave it simple problems that we understood. We didn't give it these very complex problems of, discriminate, every single, interaction in the world, right? I'll skip this. And another way to think about this is, about, let's say, less than 10 years ago, I would go to the CTP to ask them for variables to kind of understand this space. And there's an infinite, incredible amount of beautiful papers from the CTP about this, many from this guy here. And now I've just kind of trained a neural network to try to learn all the underlying patterns and kind of replace it there. I mean, it's, the thing is really, I needed to ask a theorist to kind of build this training, right? I needed to know the physics to learn. But suffice it to say, we can kind of automate this whole process. At least we see evidence that we can kind of go this direction. So what does this mean in the context of training, of teaching? So the idea then is, if you want to teach these ideas for how do you effectively use machine learning in the context of teaching something like physics, you want to take the ideas of physical knowledge and the machine learning as a tool and combine them. So the left here is a kind of deep neural network regression, where we're just trying to fit a pattern in the data. So you just give a neural network, in this case you give it kind of smeared sine data, and it will learn the functional form. And we could take the same neural network and then apply it on the right. This is actually a Higgs boson. And we can tell it, we have to tell it the right problem. So we tell it, look for the direction of the kind of particles that we missed when we looked at this Higgs boson. And it can, if you tell it the kind of look for this direction of these particles, it will actually find them, and it will give you this nice kind of narrow Higgs mass peak. So the kind of thing that we actually can use to do kind of core like particle physics measurements, right? If I had told it the wrong task, like just measure the mass, this would not have worked, right? So the neural network would have just given me a spike at the Higgs mass, and it would have been basically useless for kind of downstream tasks. And so over the kind of past 2 years, I've been trying to teach these concepts of how do you embed physics knowledge with machine learning to kind of get to the point where you can do core measurements and core kind of physics understanding. This doesn't use, ChatGPT, but this kind of goes to the guts of how we build these things. And it teaches you, how you can kind of respect physics principles and embed it into the physics. So here's an example from one of the labs where if you want to actually find kind of a bump on flat data, if you just train a neural network, it makes a bump out of the background. But if you train the neural network and you give it some sort of physics constraints, the background will not get bumpy. And so then you can look for a signal, which is this right here, which would be a bump on top of this background, as opposed to here, which would be a bump on a bump. It wouldn't work. So to summarize this very briefly, I asked this great 20th century philosopher, Yogi Berra, and he says that you can observe a lot by watching. And if you want to extend the quote, and you can tell it if it ain't doing physics. And that's kind of the idea that we should always think about when we use these kind of large language models and kind of deep learning approaches to kind of expand, inject physics. And this is the way I think we should be teaching it. So thank you.
Hi, Phil, and thanks for putting me out of business. All those papers I wrote back then, not worth the paper they're written on now. So, can you talk a little bit more about kind of implications on the more experimental side? So, like, I can understand from the data analysis side, when things are in a space where even someone like me as a theorist can understand. But a lot of the complexities of analyzing data at colliders is about synthesizing information from detectors, dealing with reconstruction, dealing with things like triggering. Like, what is the role of something like a foundation model, or what is this role by of learning things by observing? Like, how does that play in terms of experimental analyses, where at least my experience is that experimental collaborations are quite conservative in adopting these type of techniques. But what can you offer that community or
Yeah,
your community in that
so
context?
a lot of the kind of conservatism came from the fact that these neural networks, if they went out of the kind of boundary of where they learn, the problem you're trying to solve, they just go haywire, right? And kind of building these intermediate spaces and solving intermediate problems are the kind of thing where the space suddenly becomes continuous, right?
Mm.
So I have a longer version of this talk where I actually show you can kind of move around the space, and it has some sort of physical meaning. But beyond that, the other thing is that these kinds of smaller problems are the kinds of things you can actually go to data and kind of augment the data. And you can actually kind of play games where you augment the data. And so you have kind of a handle now to kind of both kind of make your simulation more data-like, but make kind of your data learn these patterns inside the data and even kind of intermesh them. I, you know, these are kind of, this is a paper I haven't even put out in the archive yet, but the point being is that I think there's a lot of kind of ideas you can play around with this that could potentially get you to something that gives you kind of physically meaningful results for not just the kind of problem you're trying to solve, but for problems that would be downstream. And I think that's where, that's my feeling where the kind of field likes to go is to kind of see if we can get a foundation model that can actually solve many problems at the same time.
So you're basically saying that going from traditional machine learning, deep learning, but now kind of the foundation model world, like the level of generalizability is such that the extrapolation problems are actually less than they had been in the past, something like that.
That's right. I mean, there's a lot of people trying to extrapolate, and I think this is the first kind of scheme that I've convinced myself where you can kind of do this in a robust, kind of physically motivated way. Yeah.